5. Relational semantics. Extended RDBMSs have deep support. Hadoop MapReduce offers indirect support, e.g., Hive. 6. Complex data structures. Extended RDBMSs provide indirect support. Hadoop MapReduce offers deep support. 7. Transaction processing. Extended RDBMSs offer deep support. Hadoop MapReduce offers little or no support. Here's a breakdown of the Lambda architecture key points. 1. Concept overview. Purpose. The Lambda architecture is designed for big data systems, organizing them into layers to handle different needs. Components. It comprises 3 main layers: batch, serving, and speed. 2. Batch layer. Function. Stores the master dataset, which is immutable and constantly growing. Process. Computes batch views, which are pre-computed summaries of the master dataset. Efficiency. Batch views improve query efficiency by enabling indexing and random reads. Challenge. High latency in creating batch views, requiring scalable systems for computation. 3. Serving layer. Function. Stores batch views in a distributed database. Capabilities. Supports batch updates and random reads to improve query performance. Purpose. Allows for fast access to pre-computed results from the batch layer. 4. Speed layer. Function. Handles real-time data processing for low latency requirements. Process. Focuses on recent data, updating real-time views incrementally as new data arrives. Integration. Merges results from real-time views with batch views to provide up-to-date information. Complexity. More complex than the batch and serving layers due to its real-time nature. 5. Design guidelines. Data storage. Store raw, untransformed data to support future analysis and improve data quality algorithms. Immutability. Ensure the master dataset is immutable, only appending data, no updates or deletions. Data units. Store data as atomic, time-stamped, and uniquely identifiable units called facts. Graph schema. Use a graph schema to enhance the fact-based model with information about the types of facts and their relationships. File structure. Follow guidelines for folder and file structures, typically in a distributed file system. These points outline how the Lambda architecture manages data at scale, while balancing efficiency, latency, and complexity. Here are the key points of the NIST reference architecture, NBDRA, for big data. 1. Purpose. Objective. To provide an open, vendor-neutral reference architecture for discussing big data requirements, design, and operations. Nature. Not a specific system architecture, but a general framework for various big data solutions. 2. Components. System orchestrator. Responsibilities. Manages policy, governance, architectural design, resources, business requirements, monitoring, and auditing. Actors. Includes business leadership, consultants, data scientists, and architects. Data provider. Function. Provides data through various interfaces, which may include raw or transformed data. Sources. Can be internal or external to the organization. Big data application provider. Role. Performs data manipulations as required by the system orchestrator, integrating capabilities to create data solutions. Techniques. Employs big data methods and techniques differing from traditional data processing due to scalability. Big data framework provider. Function. Supplies resources or services for use by the big data application provider. Evolution. Role has evolved with big data, emphasizing infrastructure, data platforms, and processing frameworks. Data consumer. Benefit. Utilizes the value-added results from the big data system. Interfaces. Accesses data through similar interfaces as those provided by the data provider. 3. Supporting fabrics. Security and privacy fabric. Scope. Impacts all components, addressing policy, requirements, auditing, and interacting with application and framework providers. Management fabric. Scope. Manages tasks such as provisioning, software management, and performance monitoring. Focus. Ensures data quality and accessibility while addressing scale and system considerations. 4. Functionality. Interoperability. Components are connected through interoperable interfaces. Business environments. Designed to support various business settings and clarify how big data solutions integrate with existing systems. 5. Development. Analysis. Developed by analyzing a broad range of existing big data architectures from industry, academia, and government. Here are the key points on big data technologies, focusing on Hadoop and related projects. 2.5.1 Hadoop and related projects. 1. Overview of Hadoop. Type: Open source Apache project. Components: Hadoop Distributed File System. HDFS manages data storage across a cluster. Hadoop MapReduce processes data by dividing it into simpler tasks, map, and combining results, reduce. 2. Hadoop architecture. HDFS nodes. Name node stores metadata about data blocks and nodes. Data node stores actual data blocks. MapReduce nodes. Job tracker schedules and distributes tasks. Task tracker executes tasks. 3. Evolution of Hadoop. YRN, yet another resource negotiator, replaces job tracker and task tracker with resource manager, manages resources. Node manager manages individual nodes. Application master manages application lifecycle. 4. Related projects. Flume collects, aggregates, and moves log data. Uzi manages and coordinates Hadoop job workflows. HCatalog metadata layer built on Hive Metastore. Scoop integrates data from various platforms. 5. Real-time and stream processing. Storm processes real-time data streams with high throughput and low latency. Kafka messaging system for asynchronous and fault-tolerant communication between processes. 6. Security projects. Kerberos provides authentication for Hadoop clusters. Apache Knox enhances perimeter security by controlling access to cluster services. Apache Ranger centralized platform for security policies, including authorization, auditing, and data protection, e.g., encrypted files in HDFS. These points cover the core aspects of Hadoop's functionality, its evolution, and various related technologies and security measures. Key points. 1. Relevance of distributed SQL engines. Organizations need tools for interactive and low-latency ad hoc analysis of large datasets. SQL on Hadoop is a trend focused on distributed SQL engines for such tasks, applicable to datasets in Hadoop and other distributed databases. 2. Examples of SQL on Hadoop systems. Hive on Tez enhances Hive's performance with the Tez execution engine. Presto, developed by Facebook, optimized for low latency and supports various SQL features. Impala offers real-time processing with low latency and high concurrency in Hadoop environments. Drill supports interactive analysis with fast processing and compatibility with various data sources. HAWQ combines Hadoop scalability with massively parallel processing, MPP, for complex queries. Spark SQL, part of the Spark framework, supports both batch and stream processing with a focus on structured data. 3. Core features of SQL on Hadoop systems. Drill, low latency, supports multiple data sources and integrates with BI tools. HAWQ, MPP engine for Hadoop, supports ODBC/JDBC, integrates with MADlib for machine learning. Hive, initially a batch processing tool, now supports interactive queries with improvements like ORC and Tez. Impala, real-time, high concurrency processing, integrates with Hive's metadata. Presto, optimized for low latency, supports queries across multiple data sources. Spark SQL, efficient for batch and stream processing, integrates with existing Hive data. 4. Comparison table highlights. SQL support, ANSI SQL or HiveQL. Latency varies from low to medium. Scalability, generally high to very high. Processing speed, fast to very fast. Use cases, varies from real-time queries to batch processing. Single point of failure, varies by system. Fault tolerance, yes or no, depending on the system. Machine learning support, varies, with some systems providing capabilities. Data visualization, compatibility with BI tools, but no native support. 5. Other technologies. Druid, a columnar store for real-time aggregation and indexing. Key points. 1. Technologies for big data analytics. Streaming analytics, tools like Spark Streaming and Storm. Data mining and machine learning, technologies include Spark and Mahout. Data warehousing, DWing example tool is Hive. Interactive ad hoc analysis ** tools such as Hive on Tez, Impala, Presto, Drill, and Spark SQL. Data flow, example tool is Pig. Note: data visualization tools have not been introduced yet. 2. Big data visualization tools. Mashup tools, Datamir, FICO Big Data Analyzer, Tableau, TIBCO, Spotfire. Statistical tools, R and SAS for visualizing big data. Other tools, Jaspersoft BI Suite, Pentaho Business Analytics, Excel, Power BI, JavaScript libraries, Python's plotting capabilities. 3. Data extraction, loading, transformation, and integration. Example tool, Talend Open Studio for big data. 4. Data mining and machine learning alternatives. Tools, MADlib, EMC Greenplum, R, MWay, Weka, Vopal Wabbit, SAS, IBM Tools, RapidMiner, NIME. Scalability. Some tools like R and Weka are not scalable by default but have extensions for big data, such as SparkR and RHadoop. Challenge. Scaling algorithms to handle large datasets effectively is a key challenge in big data analytics. 1. Systematic approach to data warehouse design focuses on a database management perspective. Includes star schemas and SQL codes for practical design and implementation. Uses case studies to explain concepts, with incremental learning through chapters. 2. Operational databases. Used for daily business activities, e.g., sales, finance, bookings. Supports business automation and processes transactions. Ensures database consistency, accuracy, and correctness in transaction settings. Provides data for reporting and supports business operations. 3. Design and implementation. Operational databases use structured designs like entity relationship, E/R, diagrams. Relational DBMS, RDBMS, can implement these designs. Suitable for transactions and querying but not for extensive aggregation or summarization needed for decision-making. 4. Data warehouses. Address limitations of operational databases by providing multi-dimensional views with pre-computed aggregates. Visualized as cubes with dimensions, e.g., time, product, location. Supports multi-levels of aggregation for decision-making, from high-level summaries to detailed analyses. The architecture enables querying at various granularities for different analytical needs.